I left off in this question right here where we found a t-score or a test statistic of -20, and we labeled the t-score at the left end of the curve down here. The next question says, what is the critical value equal? We know we're doing a one-tailed test because of our alternative hypothesis. We need to know our degrees of freedom to use the table. Our degrees of freedom is 99 because it's just 1 minus our sample size. Our sample size of 100 students minus 1 is 99. We go to our table. We go to one-tails, or one-tailed test, to 0.05. We go down the column to where we find degrees of freedom of 99. The closest one we can use is 100. So we end up with a critical value of 1.66. But this time, we ended up with a negative t-score. And a negative t-score has to be compared to a negative critical value, which means we take the value from the table and turn it into a negative number. Instead of 1.66, it becomes negative 1.66. So we'll put that somewhere on the left side of 0. Here's negative 1.66, and negative 20 is somewhere further to the left, even way further than negative 1.66. We labeled our critical value. Now we can put a dotted line above our critical value. And then we can label this area as being the rejection region. And it's 5% of the possible samples are in this rejection region. The next question says, what is the p-value equal? To get the p-value, we have to go to our p-value calculator. We type in our t-score of -20. Degrees of freedom of 99 again. Once again, we get less than 0.0001. So for our p-value, we can say the p-value is less than 0.0001. We're doing a one-tailed test because of our alternative hypothesis. And in a one-tailed test, you're actually supposed to change the p-value from this calculator because this says the two-tailed p-value is less than 0.001. So if it's a one-tailed test, we're really supposed to divide the p-value in half to get a one-tailed p-value. But if it says less than 0.001, you can't really divide that in half because it's not giving us an exact number. But if it came out to something like an exact number like 0.08, then I would actually want you to divide that in half and get 0.04 if you're doing a one-tailed test. And in the questions when you're doing a two-tailed test, I actually want you to just leave the p-value the way it is, because it is giving us the two-tailed p-value. The reason why you divide it in half is because your p-value is only at one tail instead of being at both tails. When the p-value is only at one tail and not at both tails, the p-value is only half the size, which means the p-value is half. You divide it in half to get the p-value at one end of the curve. So our p-value is less than 0.001. You can say p-value less than 0.0001. We can shade the area beyond at our t-score and further to the left, which is our p-value area. Can the null hypothesis be rejected? It can, because our t-score, our test t-score ended up being beyond the test statistic. No, I didn't say that right. Our t-score, which is the test statistic, which came out to -20, ended up being in the rejection region beyond the critical value of -1.66. When the critical value is -1.66, any number at this number of right here or further to the left is in the rejection region. So -20 is in the rejection region. So we do reject the null hypothesis. We also can reject because the p-value is less than 0.05. But if the p-value turns out to be if the p-value turns out to be 0.05 or lower, that's really just telling us that we're in the rejection region. It's just another way of finding out whether you're in the rejection region. So can the null hypothesis be rejected? Yes, because test statistic is at or beyond the critical value, and p-value is at 0.05 or lower. Can the researcher claim that the mean score of the population appears to be lower than 100? This is asking if the researcher can claim that the alternative is true, or claim that the alternative appears to be true. We rejected the null hypothesis, which means that we supported the alternative, which means that we did support the claim that the mean IQ score is lower than 100. So yes, the researcher can claim that the mean appears to be lower than 100. It's yes. I have another version of this question. This one says, a researcher wants to test if the mean IQ of the population of 200,000 students is 100. Once again, the IQ scores have a normal distribution. That's important for one part of the question. The researcher doesn't know whether the mean of the population is. The researcher doesn't know if the population mean should be lower or higher than 100. Before the data was collected, the researcher didn't have a reason or a theory to predict whether it should be lower or higher than 100. And that tells us what the alternative hypothesis is going to be. The null hypothesis is still just saying that the population mean equals the value being tested. So it's saying that the population mean equals 100, because that's what's being tested. We're testing if the population mean is 100. The alternative is what the researcher is trying to support. The researcher doesn't know ahead of time whether the mean should be above or below a 100. So all the researcher really wants to do is to support the possibility that the mean simply doesn't equal 100. The researcher isn't really interested in whether it's higher or lower than 100, or at least doesn't have a reason to predict whether it's higher or lower than 100. So the alternative is population mean doesn't equal 100. That's the third version of the alternative, which is this one down here that I showed you earlier. This is different than 100. That's basically saying the same thing as saying that the population mean doesn't equal 100. That's our alternative. Since we have this alternative, it doesn't say higher or lower. It just says doesn't equal. That means we're doing a two-tailed test. This is one is saying it's the same question that says to draw the shape, label the curve, and label the number of combinations. You can find that with the combination calculator, and label the size of each sample by putting a number in each box. We have to find out what the shape of the curve will be. The curve of the sample means. It says, in this population, IQ scores have a normal distribution, which means that the curve, this curve right here, will be normal, the normal distribution in part B. This question says, draw the shape of the t-scores of the possible samples. Label the shape of the curve, just like we did before. If we ended up with a normal distribution in part B, our curve in part C will be a t-distribution with degrees of freedom. You have to know how many degrees of freedom. So we recruited a sample of 100 students, which means the degrees of freedom is 99. So once again, this would say 99 degrees of freedom. Can the one sample t-test be conducted? We had a normal distribution in part B and a t-distribution in part C. So the answer would be yes. What does the test statistic equal? We just have to use our formula again. This time we have the mean of 106 and the standard deviation of 30. So we'll end up with this number again. We'll end up with positive 20, which means the test statistic is 20. We would want to label it again at the right end of the curve. So we have 20 out here. This is our rejection. That's our test statistic. And we can put a little box right there. A little X showing that that's our outcome is right there. We also need our critical value. This time we're doing a two-tailed test because our alternative hypothesis is just saying that the mean doesn't equal 100. It's not saying that the mean is higher or lower than 100 up here, which means we're doing a two-tailed test. We can tell by going back to part A. Now we need to go to our table. This time we're doing a two-tailed test. So we go to 2 tails, 0.05. And then we go down to our degrees of freedom. Our sample size was 100, which means our degrees of freedom will be 99 again. And we can round 99 to 100. This time we end up with a critical value of 1.984 because we're in the two-tailed 0.05 column. Um, 1.98. So we actually have, since we're doing a two-tailed test, we have two critical values actually. So you would actually say the critical value is, the critical values are 1.98 and negative 1.98. We can label both of these somewhere out here. This is negative 1.98. This is positive 1.98. We can draw a dotted line above both of these numbers. We have a rejection region down here at negative 1.98 and to the left. It's actually 2.5%. It's not 5% anymore because we're doing a two-tailed test. And the other 2.5% are in the other rejection region, which is at 1.98 or higher. This area up here is also a rejection region. And it's also 2.5%. What does the p-value equal? And it says, draw a sketch of the p-value under the curve. To get the p-value, we have to have our test statistic, which is 20. We have to go to our p-value calculator. We type in 20 and 99 degrees of freedom, and we get less than 0.001. So the p-value is less than 0.0001. We need to draw a sketch of the p-value. The p-value is at the area that's at our test statistic of 20, or further to the right here. And since it's a two-tailed test, our p-value also includes the area at negative 20, which is the opposite of our t-score, and further to the left. And you can label both of these as being the p-value. Or you could say 1/2 of p-value is over here. And 1/2 of p-value is over here. And then you could just, somewhere on here, you could say the total of the two shaded areas is less than 0.00001, because that's the p-value that we ended up with. So the rejection region is these two areas that are below the negative critical value and above the positive critical value. The p-value only includes the area right here that starts at 20 and the area down here that starts at negative 20. The rejection region includes the area starting at negative 1.98 and over this way, and the area starting at 1.98 and over this way. Can the null hypothesis be rejected? The answer would be yes, because our positive critical value is 1.98. And when we compare our t-score, which ended up being positive 20, to the positive critical value, our t-score ends up being above the critical value. It ends up in the rejection region, and also our p-value is less than 0.05, which means we can reject. This one says, can the researcher claim that the mean score of the population appears to be higher than 100? Which is what the researcher was trying to support. The researcher rejected the null hypothesis, which means the researcher supported the alternative hypothesis, which said that the mean doesn't equal 100. So the researcher supported this possibility of the mean not equaling 100, but since the researcher has rejected the null hypothesis, the researcher can make a more specific conclusion by looking at what the sample mean equals. The sample mean came out to 106, which is higher than the population mean being tested. So since the sample mean came out to 106, it's showing evidence that the population mean is above 100. Because the sample gives you information about the population. So this sample mean about 106 is showing that the population mean appears to be higher than 100. So the researcher supported their alternative hypothesis that they had at the beginning of the study, that they can also since the null was rejected, they can make a specific conclusion that the mean appears to be higher than 100. The population mean appears to be higher than 100. In a two-tailed test, if the null is rejected, you just look at your sample mean and use your sample mean to decide if the population mean appears to be higher or lower than what you were testing. The answer would be yes. The researcher can claim that the mean score of the population appears to be higher than 100. Let's see. That covers those. This one is a little bit different because basically everything will follow the same steps that the first 3 questions did, or it'll follow the same rules. The only thing one thing that's different in this question is it's saying that in this population, IQ scores do not have a normal distribution. So what does that mean? That means in part B, this shape in part B above the sample means will only be normal if the combinations are 30 or larger. The combinations have to be 30 or larger to make up for the population not being normal. So let's see if we do have combinations of 30 or higher. The researcher recruits a sample of 100 with a sample size of 100. That means that we are selecting from a curve, we are selecting from a set of possible combinations that are 30 or higher because we're selecting one of these possible combinations of 100 in our study. So since our sample size is 30 or larger, this shape in part B, this curve will still be normal, even though the population wasn't normal. Otherwise, this is similar to the first question that I gave you. In question 5, in this other question, it says, in the population, IQ scores do not have a normal shape, again, and the researcher only recruits a sample size of 20. So this means that we don't have a normal population, we're not sampling from a normal population, and our sample size isn't at 30 or larger. What that means is the curve around the means of possible samples will not be normal. And the curve around the t-scores of the possible samples will not follow a t-distribution because part B wasn't normal. And also, the one sample t-test can't be conducted because we didn't have a normal set of sample means and we didn't have a t-distribution, so we can't do the test. We didn't satisfy our assumption of having a normal population or a sample size of 30 or larger. For this type of question, all I want you to do is, in part B, say that the curve around the means will not be normal. And in part C, say you won't have a t-distribution. And for part D, say no. Otherwise, I don't expect you to answer any of the other questions in this type of problem. I just want you to realize that the test can't be run. This is my first example of an independent samples t-test. You can tell it's independent because an independent samples t-test is used to test if the means of two populations are equal. This says a researcher wants to test whether the mean IQ of one population is equal to the mean IQ of another population. That's telling you it's an independent samples t-test. what are the null and alternative hypotheses? The null hypothesis of an independent sample t-test says the means of the two populations are equal. The alternative will say that, well, there's actually three different versions of your alternative hypothesis again, just like you had with the other questions. One version says that the mean of population 1 is lower than the mean of population 2. The next one says the mean of population 1 is higher than the mean of population 2. And this last one says the means of the two populations are different. We need to see which one we're choosing. In this sentence right here it says, the researcher thinks that the mean of population 1 should be higher than the mean of population 2. That means we're trying to support this alternative, which says that the mean of population 1 is higher. So this would be your alternative hypothesis. Question B says, draw a sketch of the sample mean differences, label the shape of the curve, give the number of possible combinations of 200, and the size of each possible sample. Let's see if we can do that. Well, first of all, let's see if we know what the shape will be. This says that in this question, the IQ scores have a normal shape in both populations. What that's telling us is that this curve in part B will have a normal shape. This is a curve of sample mean differences. So you can draw a normal curve like this. just fill in the shape under the curve. How many? We have 100 people in the first sample and 100 people in the second sample right here. We've recruited a sample of 100 from population 1 and a sample of 100 from population 2, which means each of these will actually look like this. You can put a dotted line in here and put 100 inside each of these. Put 100 in each side, so you can see that it's a combination of 200 people, not just 100. We know that the shape of the curve is normal. Because both populations are normal. Now we just need the number of possible combinations of 200. We can get that with our combination calculator. What we need to know is how many people are being selected from both populations, and we need to know the size of both populations. So we know that 100 is being sampled from this population, and another 100 is being sampled from this population. We need to find out how many combinations of 100 can come from this population, and how many combinations of 100 can come from this population. So we need to go to our calculator, and type in 100 and from 200,000 again. We get the same number. So there's this many combinations right here in this population. And there's also the same number of combinations of 100 that can be selected from population 2. And the total number of combinations of 200 in here will actually be this times this, whatever that equals. So basically just take this and use this as your number of combinations. That are in here. It's because if you took 2 from 3 and another 2 things from another group of 3, you would end up with how many? 3 combinations over here and 3 combinations here, and you'd have 9 total combinations. But I can't really have you multiplying these big numbers, so I'll just have you write it out like this. So we've taken care of part B. For part C, you can just make the curve of t-scores. This time, instead of each combination being stacked above its sample mean difference, it's above its t-score. And we ended up with the normal distribution in part B. So that means that right here we're going to end up with a t-distribution in part C for this curve. We have to know how many degrees of freedom we're going to have. In an independent samples t-test with 2 samples, the degrees of freedom is the total number of people being selected, which is 200 in this case, minus 2. So 200 minus 2 is 98. It's a t-distribution with 98 degrees of freedom. That's the shape of the curve. So we've drawn the shape. We've drawn the sketch. We labeled the shape. We have our number of combinations, and we labeled the size of each sample because we put 100 in both sides of the box with a dotted line in the middle. So the sketch will just need to look like this for the t-scores. You label the shape, the number of combinations, and the sample sizes inside here, and you say it's the number line of t-scores. What else? That takes care of part C. Can the independent samples t-test be conducted? The answer is yes, because we ended up with a normal distribution in part B, and because of that, we ended up with a t-distribution in part C, which means the test can be done. So the answer would be yes. What does the test statistic equal? We have a different formula this time, because it's a different type of t-test. X bar 1 and X bar 2 are the means of the two possible samples. Not the possible samples, the mean of the two samples that were selected. Let's see what they equal. The mean of our first sample was 108. The mean of our second sample was 100. No, I mean, not 100, 104. So it's on the top of the formula, we have 108 minus 104. On the bottom, we have S1 squared is the standard deviation of the first sample squared. The standard deviation of our first sample was 2. So it's going to be 2 squared. Over N1, which is the number of people in sample 1. The first sample of 1 had 100, because the researcher recruits a sample of 100 from population 1, which means the first sample has 100 people. It's 100. S2 squared is the standard deviation of sample 2 squared. The second sample had a mean of 104 with a standard deviation of 3. Three squared over the number of people in sample 2 is 100. Because right here it says 100 students were selected from population 2, meaning the second sample had 200 people. Now we should do the bottom part first. 2 squared is 4, and that's over 100. 3 squared is 9, and that's over 100. And that comes out to 13 over 100. The square root of 13 over 100. If we divided 13 by 100 in a calculator, we would get 0.13. And the square root of 0.13 is, let's see, 0.36. The bottom of our fraction is 0.36, so we have 4 over 0.36. What does that come out to? 11.11 if we round it. We can go over here to our sketch in part C and label our test statistic, which was 11. The middle is 0. 11.11 would be somewhere toward the right end right here. We can put an X above it, showing this is where our data set, our sample comes from. Our test statistic equals 11.11. And we already drew the sketch of it. This says, what does the critical value equal? To get our critical value, we need to go to our table again, which means we need to know if the test is one-tailed or two-tailed. These two alternate versions of the alternative hypothesis that say higher and lower are go along with one-tailed tests. The bottom one is two-tailed. So since this was our alternative hypothesis in part A, we're doing a one-tailed test. We also need to know what our degrees of freedom are, so we can use the table. We have, this is the wrong one. We had 98 degrees of freedom. Was that correct? I'm sorry. It's 100 plus 100, which is 200, minus 2. The degrees of freedom is actually 198 for this test, because in a t-test with two samples, it's the total, which is 200 minus 2. So let's go to our table. We have 198 degrees of freedom, which is pretty close to 200. So let's go to one tail, 0.05. Let's go down here. If we round it to 200 degrees of freedom, we get 1.65 as our critical value. Let's see. And we ended up with a positive outcome of 11.11 for our t-score, which means we have to use a positive critical value. Critical value is 1.65. We can label the critical value in our sketch. .65 is somewhere up here above 0. If I really wanted to make this sketch accurate, 11.11 would be way up here somewhere, much high above the critical value, but it's difficult for me in this sketch to really make it accurate like that. So this is 1.65, our critical value. We can drop these dotted line above it, and we can label this area as being our rejection region. We're doing a one-tailed test because of our alternative hypothesis in part A, which means that the entire 5% of the rejection region is in this one tail of the curve. So it's a 5% rejection region. What does the p-value equal? We have to go to our p-value calculator. Our test statistic was 11.11 with 198 degrees of freedom. Comes out to less than 0.0001 again. So our p-value is just this area at 1.11, which is our t-score, and further to the right. It's a one-tailed test, so we only shade one end of the curve for the p-value. And in a one-tailed test, you're actually supposed to divide this number in half, since your p-value is only at one end of the curve instead of two. But we can't. It's hard to divide this number in half. So this is the p-value. P-value is less than 0.0001. We drew our sketch and we labeled the p-value. Can the null hypothesis be rejected? It depends if our t-score reached the rejection region. Our t-score was 11.11, and it is in the rejection region because it's above 1.65. It's beyond 1.65, and our p-value is less than 0.05, so we can reject. Can the researcher claim that the mean IQ of population 1 appears to be higher than the mean IQ of population 2? Our null hypothesis that said that they're equal has been rejected, which means we did support our alternative, saying that the mean of population 1 is higher than the mean of population 2. So the person can make that claim. So it's yes. And then this other type of question, it's just a different version of the same question. This one says, the researcher thinks that the mean of population 1 should be lower than the mean of population 2. That tells us what our alternative hypothesis is going to be. Null hypothesis is just the possibility that the population means, or the means of the two populations are equal. Our alternative is what the researcher is trying to support, which in this case is the possibility that the mean of population 1 is lower than the mean of population 2. And we have a one-tailed test again, because whenever it says higher or lower inside this alternative hypothesis, it's a one-tailed test. Part B and C are the same question as before. It's the same question where we did before, where we drew these boxes with 100 on each side, and we wrote this as our number of combinations, and we labeled the shapes, and so B and C are the same as before. This is how you do it with an independent samples t-test. And we're still doing an independent samples t-test. Can the independent samples t-test be conducted? We have to check a few things. The mean IQ score, the IQ scores of the students have a normal shape in both of the populations, which means that the shape in part B of the sample mean differences will be normal, and the shape in part C with the t-scores will have a t-distribution shape, which means that the test can be done. So it's yes. What does the test statistic equal? We have to calculate it with all of these numbers. You have to subtract the two sample means on top, which will be 102 minus 106, because the mean of the first sample is 102, and the mean of the second sample is 106. We have to find out what our standard deviations are again. The first sample had a standard deviation of 2. The second sample had a standard deviation of 3. And both samples had 100 people. So it's 2 squared over 100 plus 3 squared over 100. which ends up being 4 over 100, plus 3 over 100. It ends up being the same as before. So the bottom of our formula comes out to same it did last. It comes out to the square root of 0.13 again. Which was 0.36. And the top this time is going to be 102 minus 106, which is negative 4 over 0.36, which comes out to negative 11.11. The test statistic equals negative 11.11. And we need to draw the test statistic inside of the curve in part C. We have this is going to be different this time because our test statistic is down here at negative 11.11. So I'll just, I just need 1 second. Our test statistic is down here at negative 11.11. And we can draw an X right here to show that this is where we collected our sample from, our 2 samples. What does the critical value equal? We have to go to our critical value table again. We know we're doing a one-tailed test because of the alternative hypothesis, which said lower, which had the word lower in it. And we know our degrees of freedom came out to 198 because 200 people minus 2 is 198. So we have to go to one tails up here, 0.05, and then go down in this column where we get to 198 degrees of freedom. Which is close to 200. So we get 1.65 again. But this time, we have a negative t-score, so a negative t-score has to be compared to a negative critical value, which means our critical value will actually be negative 1.65 this time. This isn't our rejection region anymore. Our rejection region is at 1.65 and to the left. And it's a one-tailed test, so it's 5%. This is what does the p-value equal? We need to go to our p-value calculator, type in our t-score, which was negative 11.11. Our df is still 198. Still comes out to less than 0.0001. When we draw the sketch of our p-value, we make, this time, it's a one-tailed test, and our t-score was negative 11.11, so the p-value is just this shaded area that starts at negative 11.11 and goes further to the left. So we can say this is our p-value. And it's less than 0.001. Can the null hypothesis be rejected? Our t-score of negative 11.11 ended up in the rejection region because it's in this area that's at negative 1.65 or further to the left. So it's in the rejection region, and the p-value is 0.05 or lower. So we do reject. And since we rejected the null hypothesis, the researcher can claim that the alternative appears to be true. The researcher hasn't proven that it's true, but a person can claim that it appears to be true. And the alternative says that the mean of population 1 is lower than the mean of population 2. This is a possibility that's been supported, so we can say yes. This is another version of that same question. This time it just says the researcher doesn't have an idea about which population should have the higher IQ score, higher mean IQ score. That tells us what our alternative hypothesis is going to be. The null hypothesis says that the means of the two populations are equal, the alternative says the means of the two. This time it'll just say the means of the two populations are different, because the researcher didn't have an idea about which population would have the higher mean. So this is the alternative that the researcher is trying to support. And since this is the alternative hypothesis, and it doesn't have the word higher or lower in it, it's a two-tailed test. Part B and C are the same. Can the independent samples t-test be conducted? This says, right here, the IQ scores of the students have a normal shape in both populations, which means in part B, the shape of the sample mean differences will be normal, and the shape of the t-scores in part C will have a t-distribution. So once again, the test can be done. To get the test statistic, you use the formula. This is back to 106 and 100. Wait, this says 106 and 100 this time. So what would that equal? No, it's not. It's 102 and 106. Those are the two sample means. So it comes out to, t-score comes out to negative 11.11 again. We need to label it in that graph that we made for part C, which we have right here. We need to put an X above it to show that that was our outcome. And to get the critical value, we have to go to the critical value table again. We know we're doing a two-tailed test because of the alternative hypothesis. It doesn't say higher or lower. And we know our degrees of freedom is 200 minus 2 because of our sample sizes. So when we go to the table again, we go to two tails, 0.05. We go down to our degrees of freedom. Which is close to 200. This time we get 1.97 as our critical value. And we're doing a two-tailed test, so actually we have two critical values. So you would say the critical values are negative 1.97 and 1.97. We need to label both of them. Our t-score is down here at the negative end this time. We have our other critical value up here at 1.97. We draw another dotted line up here. We have a rejection region at the left end that's 2.5% because it's a two-tailed test. And we have another rejection region up here, which is also 2.5%. We need to label both of them. So we labeled our critical value and our critical values, both of them, and the two rejection regions. What do we do now? We have to label our p-value. To get our p-value, we have to type in our t-score into the p-value calculator. It's still negative 11.11 with 198 degrees of freedom. And it comes out to 0.0001, less than 0.0001. Since we have a two-tailed test, our p-value is at both ends of the curve, meaning our p-value is at the area at negative 11.11 and to the left, and also the area at positive 11.11 and to the right. We have to include the area in the opposite tail too. So here we can put, somewhere up here we can put above 1.97, we can put positive 11.11, which is the opposite of our t-score. And then we can shade the area beyond it like this. And then we can label both of these as being the p-value. Or you can label it as, this one is 1/2 of the p-value, because it's really only half of it. And this is 1/2 of the p-value. Because these two areas add up to our p-value. Now you can say, something like, the total of the two shaded areas is less than 0.0001, which is what the p-value calculator gave us. Can the p-value is less than 0.0001. Can the null hypothesis be rejected? We're in the rejection region because our t-score, which came out to negative 11.11, is in the area that's beyond, what is it? It is in the rejection region, and it's beyond the negative critical value down here. Our t-score ends up in the negative rejection region. It's at negative 1.97 or lower. So we're in here, so we can reject. In a two-tailed test, we also have a rejection region at the other end, which means if we ended up above 1.97, we would also be able to reject up here. But we're in one of the rejection regions, and our p-value is 0.05 or lower, so we do reject the null hypothesis. And it says, can the researcher claim that the mean of the first population appears to be lower than the mean of the second population? The researcher was able to reject the null hypothesis that they're equal, and which means that the researcher supported the possibility that they're different. And now the researcher can look at the data set to find out exactly which way they're different, meaning exactly which population appears to have the higher mean. The first sample had a mean of 102. The second sample had a mean of 106, which means the sample of the first population had the lower mean. So that means that the null hypothesis is rejected. So we're saying that they're not equal, and because of the sample means, it appears that the first population has a lower mean. So in a two-tailed test, after you support your alternative hypothesis, you look at the two sample means and decide which exactly what the difference is, if 1 is higher than 2 or if 2 is higher than 1. So yes, the researcher can claim that the mean of population 1 appears to be lower. What does this say? This is another version of the question. This time it says the IQ scores do not have a normal shape. But it also says that the researcher recruits a sample of 100 students from each population. So the sizes of the two samples are 30 or larger, which means it actually doesn't matter that the IQ scores in the two populations aren't normal, because our sample sizes are at least 30. Which means once you get to part B and part C, the shape in part B will be normal with the sample mean differences, and the shape in part C will have a t-distribution curve, because even though the populations weren't normal, we had sample sizes of 30 or larger, which means we do end up getting these two shapes that we want. Otherwise, all these other questions are the same as before. This last one says, a researcher, well, it says, the IQ scores do not have a normal shape in both populations. And it later goes on to say that both the two samples only include 20 people. There's only 20 people in each of the two samples. So we don't have the normal populations. We're not sampling from normal populations, and our sample sizes aren't 30 or larger, which means that since neither of those are true, these two shapes in part B and C won't be the right shapes. We won't have a normal shape in part B with the sample mean differences, and we won't have the t-distribution curve in part C. What that means is the shape of part B won't be normal. The shape of the sample mean differences won't be normal. The t-scores won't follow a t-distribution. And the test can't be conducted. And that's all you have to say for this question. You don't have to answer any of the other questions because you just can't do the test. And I think that covers all of the questions that I might give to you in this homework assignment. Um, just let me know if you have any questions.